but that's life in Maine in the winter. There's one demonstration I've not done with you that had to do with pressure, so it's going to be kind of a repeat. And it has to do with the ideal gas law. I have a piston here, and I'm going to push very strongly on the piston, and there's a piece of, what would I call it, a cotton ball, a tiny piece of cotton ball on the bottom. And pushing it very fast, I'm going to increase the pressure. I'm going to decrease the volume some. But what happens on the right-hand side of the ideal gas law? Anybody remember? PV equal NR. So NR are two constant. What about T? What's T? So temperature is going to go up because I'm going to do it so fast. So it's not going to be as we did in the lab slowly with the masses that we put on the syringe, but we're just going to compress, and P times V is going to be about equal. Here, I'm going to do it fast enough in the piston that temperature is going to go up. This is what happens in your car as well, in the pistons in your car, to ignite the fuel. And hopefully I'll be able to ignite this piece of cotton. It doesn't work every time, so let's see if it will not work. I'm just trying to do it high enough that everybody can see it. Well, maybe it's going to work here. So I'm going to just push very fast, and when it works, you're going to what you see is a spark. Okay? There's some smoke I see coming down, but I don't see a spark yet. Maybe I'll try to get the piece out. Maybe if I do it with a smaller piece. This one is a relatively large piece. It works better. Let's try again. See, it doesn't always work. Things don't always work the way you want them. Okay, smaller piece. And maybe we'll get Oliver to be closer to me so he can attest that actually there's something happening. Okay. Oliver, can you come here? Just on the side, just so that it's not going to look like I'm full of it. Okay, it's down below. Okay, I'm holding it, trying again. You see? So you can go fast enough that you can ignite something by pressuring air enough so the temperature goes high enough to ignite. Excellent. Whew. It's always kind of a what's your name? Remind me.
Me?
Yeah. Courtney. So you're not one. The two that came. Are you in the last lab today?
No.
No, you're not either. So doesn't have to do with you. We're canceling the last lab, so I'm trying to recruit everybody to the first two. So it's going to be a little more cozy. Okay, so back to what we talked about. We talked about two important concepts. Hydrostatic pressure, where simply the weight of a fluid divided by the area underneath provides pressure. There's no motion in that case. We'll add motion today. And then we talked about continuity, the fact that if I have fluid going through whatever it's, a vessel, if the vessel constricts, and I'll show you a video of it today, the fluid has to go faster to maintain the same volume flux across it. And the reason we can assume that is because water is highly incompressible. So the same volume going through here is approximately the same volume going through here. And so we can think of mass conservation and volume conservation as being the same for an incompressible fluid. Okay, today we're going to move to another concept that's very important in fluid that has to do with Archimedes' principle. So the way some of you might have heard about it is that the buoyancy force acting on a vessel equal to the weight, so the weight is mass time gravitational constant of the fluid that it displaces. Okay, so if I have a vessel in the water and it's floating on the water, gravity causes this boat, as an example, to lie down in it, and then when it's floating on the top, and it's in equilibrium, nothing is moving, everything is at rest, that force of gravity has to be equal to the force of buoyancy, which is the volume displaced, so just this area that's underwater, times the mass, which is the density, the volume displaced times the density of the water displaced, that's the mass of the volume displaced, volume times density, times the gravitational constant. Okay? So this is what happened when you float. What do you think happened when you're underwater in terms of the buoyancy force? So this is your floating object. Now I'm putting that object underwater. It's here. And let's say it matches the density around it, so it doesn't sink. What's the gravitational force acting on it? mg. And what's the buoyancy force acting on it? Just the same. It's the volume of the object times the density of the displaced fluid times gravity. That's the buoyancy force. And that always acts on any submerged object. And those of you who dive know that it's much easier to lift things underwater than it is in air. And it is easier because the buoyancy force works for you. Now, where does the buoyancy force come from? What's the origin of that buoyancy force? Think about how pressure is distributed in the water. Pressure, hydrostatic pressure, increases as you go down. Okay? And we talked about the fact that force or fluid flow from high pressure to low pressure because there's a force associated with the pressure. So if you integrate the pressure on the area of this, in order to get the net force on this object, you're going to get, because the pressure here is higher than the pressure on the sides, you're going to get a net pressure, a net force due to this increasing pressure in this direction. And this is the origin of the buoyancy force. It's the fact that pressure increases with depth. So this is for a floating object. We did the balance for a sinking object as well. So even if this was sinking, and this is what happens if your density is bigger than the density of water, you're going to sink, as we saw in the lab about density. There is this buoyancy force acting on. That's reducing what you get as gravity. Okay, there's other concept we need to talk about. Something called the center of buoyancy. Center of buoyancy is the center of gravity of the fluid you displace. So if you displace fluid, and let's assume it's all of the same density, it's simply in the center. And we have something that's called the center of gravity. And that's, again, we're looking at everything that's in and how it's distributed within that object. And we're simply summing up this center with gravity here added. So it's all the masses associated with an object and their distances from any common coordinate system. And simply that will give us this center of mass. Now it turns out if your center of gravity is deeper than your center of buoyancy, so if we talk about an object and we have a center of buoyancy here, that means that the buoyancy force acts as if it was all working on a mass that's concentrated here. And now we have, let's say that we have more, this density in the object is bigger than the rest of it, so the center of gravity is lower. If I displaced it sideways, it will right itself right up. But if I have the opposite case, where I have a center of gravity that's higher than my center of buoyancy, this wants to go, this is the center of the forces going in this direction. Gravity is in this direction. This is going to tumble. And with the stable state, which is when the buoyancy force, the center of buoyancy, the BC, is higher than the center of gravity. G, or we can call it C for center. That's going center of buoyancy here and center of gravity here. This is the center of buoyancy above center of gravity. So this is the stable case. Now there's several situations where it can become important. One of which is obviously if you have a floating object and you're putting a lot of mass right on top, you're raising the center of gravity, while the center of buoyancy is right at the bottom. And this becomes very unstable, as you can imagine. You can also see it with organisms. Organisms that particularly people have seen it with things like dinoflagellates and kelp. But dinoflagellates are these organisms that have a flagella. Some of them are photosynthetic, some are not. But they like to migrate, and they migrate with response to light. And one of their way to stay in orientation towards the surface or the opposite direction, depending on what they need, is to have a center of buoyancy and a center of gravity that are not co-located. There's a difference between them, and the difference is such that the center of buoyancy is higher or lower to the center of gravity, depending on if they want to go up or go down. So they use these forces to right themselves in a fluid in a specific direction. And you do it in a cell by accumulating denser material in one part of the cell and less dense material in another part of the cell. Less dense might be lipids and things like that. Another example you may think of is a kayak. I don't know how many of you kayak, but kayaks are inherently unstable. And one way by which you make them more stable when you roll, you do kayak rolls and things like this, is by reducing your height relative to the hull. And in a kayak, the center of gravity is higher than the center of buoyancy in many of them. And so you have to maintain, maintain position as much as you can, such that there's not a strong torque that's trying to roll you over. A ship is much more stable because the gravitational constant is higher than the buoyancy. Most ships. I mean, they're built that way in order for them not to keel over. Okay, some buoyancy issues associated with marine organism. Some of the material that organisms are made of, such as blubber, is less dense than water. So that will result in a stronger buoyancy force. Muscles and bones are denser. And air is obviously buoyant, and it's also compressible. So as you're changing depth, you're going to change how buoyant you become. And that's an important aspect of the fact that air does compress and less. Again, the buoyancy force is not based on how pressurized the air, it's based on how much volume it takes. And it will take less volume as you dive down for the same amount of air. So here are some strategies that marine organisms deal with adjusting their buoyancy so that they don't have to work hard against gravity. If your buoyancy force is exactly the same as the force of gravity, there's no net force on you to go up or to go down. You can maintain the same level without having to flip all the time, without having to work. So what organisms do, for example, is add some air in their stomach. Some sharks do that in order to adjust their density. Many fish have swim bladders. And that's physiologically regulated, so they will not have to fight gravity in the water. And in sharks, there are also large oily levers that adjust their buoyancy, or at least help them offset bones and muscles so that they don't all the time have to fight. They don't have to fight gravity in order to stay at the same depth. Now, we're not the same. People are not the same. So when we dive, we have equipment that's extremely buoyant, particularly in Maine, where we dive with dry suit or with thick wetsuit. And so we need to put weight belts in order to help us maintain depth to start with. And then we have these devices that we put on us to compensate on a smaller adjustment at different depth. So we fill it up with air. It's connected to the scuba bottle, and that allows us to either put some air in it if we want to increase our buoyancy, or get the air out if we want to decrease our buoyancy. And if we want to lift things from the bottom, we use what's called lift bags. That's what this person is carrying. That's what you see here, which we attach to object in the bottom. We fill them up with air, and that allows us to detach them from the bottom and take them from one place to another. Again, once you filled it up and you go up, the extra air that takes more volume is just going to go sideways. It cannot contain more air than what's in there. But if you put a little bit, that will increase in volume and will make it more and more and more buoyant as you go up. So you have to be very careful. Similarly with these devices, as you rise of a deep dive, you have to continuously readjust the amount of air in it, because you're getting more and more and more buoyant simply because the air is expanding, increasing the buoyancy force acting on you as a diver. We also use it nowadays with many, many robots that we distribute in the ocean. So there's two flavors that you may have heard of. The most common one are called the Argo float. And what is done in them is that there's a compressurized tank inside with oil in it, and outside a balloon. And what is done is to, with an active pump, to pump oil into that balloon that's here or out of that balloon. And what we do in the process is change the volume of this object. Oliver, you may want to hear about it. And so the mass is fixed. There's no change in mass, but you're changing the volume continuously, and as you go up or down. And when you change your volume with mass constant, what do you change? What property of that object do you change? If you change volume but not mass, because mass is conserved, what can you change? Density. You're changing your density. If you're denser than water, you're going to sink down. If you're less dense than water, you can climb back up. It's a very ingenious way to make an object go up and down in the ocean without using motors. Once you're at the surface, you have sensors attached to it. They collect data. You get to the surface, you send your data to satellite. They go straight to data banks, and so on and so forth. About every 10 days, they profile. And nowadays, this is from yesterday, 3,800 of these are roaming the ocean. So every day, we're getting about 383 profiles of salinity, temperature, and depth. I've been part of a group that's pushing very strongly to add other sensors to these to measure properties like phytoplankton, chlorophyll A pigment distribution, and scattering. And other sensors people have added are oxygen and nitrate. Now, so there's a very small subset, order 50 floats, that have these extra sensor on that are now profiling up and down the ocean. But it's an increasing part of the fleet. And you can download these data. They're available to any of you. And I know people who were part of the MATLAB class with Andy Thomas have used those. Additionally, there's an even more ingenious device than this one that works very much the same, except it has two wings. 2 wings and a rudder that you can adjust. And so rather than simply going up and down and drifting with the currents, this one you can direct to a specific direction in the ocean. They're called gliders. Ocean gliders. Same idea with buoyancy. You can adjust its buoyancy so it changes, it goes up, it goes down. But now you can also direct it to where you want to go. It can go up to about 1/4 of a meter or half a knot. So you cannot find extremely strong currents like the Gulf Stream, but you can fight smaller currents by heading towards them and crossing them. And nowadays we have a whole fleet of these that are patrolling around the US collecting data continuously. And again, every time they get to the surface, this is the antenna that sends data to data banks. So we send them out before storms, we send them out to simply patrol. And what they provide is data that gets into models like the weather models that we use to predict when we're going to get snow, et cetera, et cetera. All these are fed by this network of sensors, without which we'll have just big holes of what's happening here. We'll have a few tracks where ships are out in sea sending data in, but nothing like what we're getting today. So this is a real revolution in oceanography. It's the biggest change in oceanography that happened in the 90s. 90s and the first years of the 2000s. Okay, now let's talk a little bit about energy, and we're going to get to the Bernoulli principle. Some of you know about it, some do not. Energy from the class you're taking now, or you've taken it before, is simply the capacity to do work. And work is force times distance. So it has, they have the same unit. It's how much work can you do. So the energy you have in a battery, again, can be translated to work. And work has units of, anybody has an idea? Or energy? Joules. Kinetic energy is simply energy associated with motion. So mv squared over 2. We have potential energy that has to do with your height, mgh. And again, remember, this is very similar to, we talked about in the lab, to hydrostatic pressure, which is rho gh. This is simply, pressure is potential energy, hydrostatic pressure, divided by volume. And then we have this thing called pressure volume energy. It has to be with the compression of a body. And it's very important as well. There are other forms of energy. There's light, there's heat. We're going to get to heat in the near future. Internal energy having to do with chemical state that you are. And the conservation of energy principle basically state that energy doesn't get lost. You can convert it from one type of energy to another, but you're not losing it. It's conserved at any given time. Now, friction is a form of energy where you're taking mechanical energy, or in this case kinetic, and changing it to heat, and you can feel it yourself. You do this and your hands heat up. And if we look at conservation and energy in a fluid, neglecting friction, we're going to get that kinetic energy, potential energy, and this potential, the pressure volume energy are all constant. And this is very important, because it means that we can pass energy, energy will pass between these terms and stay, if we neglect friction, approximately constant. Now, if I take these and divide them by mass and look at energy per unit mass, and why would I want to do it? I want to do it because I don't want to deal with all the fluid. I want to deal with what happened to a fluid as it goes around. So I don't follow a specific blob. I follow along a path line in the fluid what's happening. So normalizing by mass, I get V squared over 2, I get GH, and I get pressure over density. Because mass is volume divided, volume times density. So I get pressure here, and this is pressure that's associated with the movement of the fluid. I have GH, which is the pressure associated with simply the hydrostatic, the fact that the fluid is there at rest. And then I have kinetic energy that's also associated with the fluid. And this is what's called the Bernoulli principle, the fact that these three have to stay constant along a fluid when friction can be neglected. Again, small v is velocity, big V is volume. Try to be consistent with what you'll find in books. Okay, so this holds only along streamline. That's mean only following a parcel of water as it goes along. And it also means that I can convert kinetic energy at one place with pressure somewhere else along the fluid trajectory. And you can find it in the literature with many different this is per unit mass conservation energy, this is per unit volume, and this is dividing further by the gravitational constant. And this is when you'll hear about pressure head that has to do with this H here, that pressure, etc. And here again, this is hydrostatic pressure, this form. So this holds in a fluid at rest. And then when we move, for example, when we squirt, actually it's coming up, so we'll talk about it in a second. When we squirted from the tower in the lab, we converted this into this. Remember? We moved from this to here. Now, how would pressure change, just based on Bernoulli principle, as we go through this constriction? Remember, we talked about the fact that velocity will increase from here to here. But how would pressure change, based on what we just saw? Let's go back. So, oh, sorry, I'm going the opposite direction. I'm increasing the velocity as I go through the constriction. What's going to happen to the pressure in the fluid? So now, there's no H. It's all in the same level. So I'm not changing H. what's going to happen to pressure along? If this is constant and I'm increasing the velocity, what should happen to the pressure? Any idea? What? It has to decrease. So simply from Bernoulli principle, we'd expect that pressure here will be lower than pressure here. Okay. Now, you may not believe me, so let's watch it in a movie. This is one of these.
The settling chamber, the nozzle, and the test section. My colleague Charles Kahn is inserting the static pressure manometer.
So they're using these manometers simply to tell us
Now he has started the flow.
how strong the pressure is in these. And you will see in a second that the height here, the height in the white part is higher.
From the upstream section to the downstream section.
So there's a decrease in pressure as the fluid
What about the
decelerates.
velocity of the flow? Since water is nearly incompressible, the volume flow entering the contraction must equal the volume flow leaving, or else mass would be created or destroyed.
So volume here is equal to volume here.
The volume flow is equal to the average velocity times the cross-sectional area.
Just like you needed for your homework. Velocity times cross-sectional
Should
area.
produce a velocity increase.
So this has a higher velocity and from Bernoulli's principle, less pressure.
The velocity field is shown here in half of a symmetrical contraction.
So here they simply divided it to half and they're visioning the fluid.
Each fluid patch accelerates and shows the velocity increase.
So here you can see the acceleration of the fluid as it goes.
Because of this velocity gradient, the front edge of each patch moves faster than the rear edge, and each patch stretches out.
The front moves faster than the lower part.
And the flow is two-dimensional. So the area of each patch cannot change, and it becomes thinner as well as longer.
Area is equal as it's going faster. Any question about it? These are very important concepts in terms of understanding what happens to fluids. Okay, we saw demos. I have some demos for you. So it's been a while. So here I have a contraption, which reminds me a lot of a manometer that we played with in the lab. And I'm going to blow air through it. And it's going to go through a wide section, a thin section, and a wide section. So which one will have, just based on what we just talked, I'm in the wide section, high pressure. Fluid going slower, pressure is higher than in the constriction section. And again, the opposite happening here. So where would the pressure be highest? These two sides, lowest in the middle. What will it do to the fluid? If the pressure is higher here and less in the middle, what's going to happen to this fluid? Pressure is high here, lower here. Fluid moves from high to low pressure. So it's going to get sucked towards the middle. This makes sense? Let's see if indeed that's what happens. Okay? Can you see it? The restoring force is gravity, so it's holding it from spilling out. But now these are not exactly equal because there is some loss of head or some loss of pressure due to friction along the way. But in both cases, they're lower than the middle one. Okay? Okay. Now we're going to do something else. I'm going to ask Oliver, if you wish, to try and fill this balloon. Try to fill it the regular way you'd fill a balloon. Let's see how effective you are. It's not very effective. It needs at least four or five full lungs, even more. We're at 8. Now let's try and use Bernoulli to do it. Okay, hold it open. How would you do that? No, just all the sides open. Just all them open, yes, like this. And how would you reduce pressure right in front of the hole so that air from all the sides will rush in? What would you do? If you want to reduce pressure, what do you have to do with speed? Okay. You have to increase it. So try now by simply, try blowing into the entrance from away. You see how fast you filled it up? And it's not that his lungs have any more air in them. It's that it's creating a low pressure point right at the entrance, and more air is running from all the sides. More air is rushing in from the sides to do it. Want to do it one more time? So Bernoulli is useful sometimes. I'll show you some other examples. Okay. So this is an example of how we could use it to sense velocity, and it's used on most airplanes you fly on. So if I have a tiny constriction here where fluid is trying to get in, here I have, this is air, and here I have, say, a fluid like water. So I have a liquid. If I have air flowing into here, it's going to change the pressure in this system. And now I'm going to get a dynamic pressure that I can use to tell me something about how fast the fluid moves. This is called a pitot tube. Or even if this is air in rest that is capped, we don't let it come in anymore. Simply by looking at changes in pressure associated with fluid moving, we can calculate what the velocity of the fluid is going to be. And here we can have it, another way to do it is by looking at the pressure at this point, which is associated with the moving fluid. So there's a drop of pressure here, compared to pressure right here, and the fluid, the air is moving in this direction but not inside. So comparing these two pressures, this one is static, and this is the total pressure, static plus the one associated with the movement of air, will give me, the difference between these two will give me an indicator of how fast the airplane is moving relative to the air around it. This is called a pitot tube. Practically every airplane has it, and when you go at the Bangor airport, international airport, before you get on the plane, look on the side of the plane. You'll see this little thing that's sticking out from the front of the plane, and it's pointing the direction to which it's going. It's not pointing to the back; it's pointing to the forward, because this is the velocity you want to measure. Going back to the squirtium columns, remember, again, conservation of energy or Bernoulli principle, both will tell you that what you're changing, and this is going to be in your homework for next week, you're converting potential energy into kinetic energy of the fluid coming out. So this is static, nothing is moving in, or very little is moving in, and this is all kinetic. But now since it's not in an enclosure, the PV term stays zero. And in hydroelectric dams, this is what we take advantage of. We take the potential energy of the fluid that's high and making it flow and generate energy with. So all hydraulic systems are to generate electricity. The hydroelectric system take advantage of this potential energy in the fluid to drive something, to cause to have a turbine that rotates. And you might know, in the Gulf of Maine, in several places now, we do it with tides. We use the tides to drive. And in the case of the tide, again, it's the pull of the moon that causes water to move and accumulate in different places, increasing its potential energy compared to what it had before. So there's something that's providing us with this energy. And you may ask, okay, since we're taking energy from the moon, Earth system, and we're piling water, we then take the energy out of this water to make electricity with. There's no conservation of energy. What's going to happen with the Earth-Moon system? And that's even much more true with all the dissipation of energy that happens with tidal currents simply running on the bottom, no sleep condition, friction all the time, thousands of years. So how would you explain that? What would happen to the moon Earth system simply from the fact that we're dissipating continuously a lot of the energy associated with the tides? Any idea? Well, it turns out the moon is getting further and further away from us because of this dissipation. You may have not noticed it. It's going to take many thousands of years, but the moon is slowly getting away from us partly because of the dissipation of energy of the tidal system. Okay, so now thinking again about water tank and pressure. Again, if I think about Bernoulli, I have my static head, I have my dynamic pressure, I have my velocity, and one can analyze along a discharge what's happening to each one of them. So here everything is static, I only have this. Here I have velocity, water is flowing, and therefore when I measure the static pressure, I'm going to have a deficit compared to what I have here. That is all due to the fact that we have velocity going on and then some losses possibly due to friction. But the sum of those, if I neglect pressure, the sum of everything between these points, if I neglect friction, between here and here should be the same. There's no loss of energy unless there is. Okay. Some other applications. What happened in terms of pressure distribution on the bottom or on top of your house as air flows on top of your house, as air flows in the ocean as current flow along the bottom. So current flows along the bottom and come up to a constriction. What happens to the fluid right here compared to the fluid here? Is it flowing faster or slower than here? It's flowing faster because, again, we're constricting these flow tube or flow lines along which the fluid is going. So if it's going faster, we're going back to Bernoulli, what happened to pressure? It drops. If pressure drops here, you'll have a change of pressure along here within the sediment, less pressure here than here, and you're going to get water irrigating into the sediment. If you think about your house and you have a chimney right on top of the chimney there's low pressure. And that's good because that will cause, on top of the buoyancy from your hot, from your fire, the fact you both provide air will going to go up because it's more buoyant, but also because pressure is such that the air is going to be sucked from your house and go out the chimney as opposed to the other way around when there's wind. So let's look at what happened in sediment. Indeed, when you do these studies in sediment, and here what they did is take tiny particles and provide them with tiny colored particle in a flow. What they found is that indeed there's a net force to bring them inside the sediment. This is very important for marine organisms that live in sediments, because if we thought of sediment as impermeable, this organism would die from lack of oxygen very fast. And this allows supply of nutrients, it allows supplies of oxygen inside the sediment. And this is on order of a few centimeters, but it's already very important, particularly for benthic diatoms and other small critters. So we tend to think of sediment as being a barrier where water doesn't go through. It does, and this change in pressure along it, and some change in pressure can simply be due to to the wave action, do cause water to go and irrigate these sediments. So today we covered the following topics. We talked about buoyancy, talked energy conservation, we talked about dynamic pressure, the pressure associated with motion. Are there any questions? Anybody here has a problem to be in the lab today? Between 2 to 4 or 4 to 6? Okay, excellent. And we're recording we recorded this lecture. All of those recordings are going on the web. Slowly we're accumulating everything, and hopefully within next week we'll have a place for you. If you want to look again at an old lecture, you'll be able to. Not I think that it's going to be that interesting, but who knows. Anyways, thank you.